Hi everybody, I think you should know the name Robert S. Hildebrand. Bob Hildebrand lives in Tucson, Arizona, and yesterday morning I dropped in for a visit. Sat in his backyard and interviewed Bob for about an hour or so. I learned a lot, and I'm hoping to share the interview with you. For a little bit of context, Hildebrand's been publishing almost every year for the last 15 years on the North American Cordillera, meaning all the mountains, all the crust from Alaska down to Mexico. And he has some radical ideas, some brand new ways to think about the building of the Rockies and everything else, including the North Cascades. I don't know how much of it's right, but it sure is interesting. And just the figures alone, the maps, the diagrams, the tables, the compilation of all sorts of data, it's really interesting to me, and it fits in nicely with the kinds of things I've been trying to do. So I wanted to learn more about Bob directly from him, and we'll see how far we go with this. But you should know about Hildebrand, and here he is.
Yep. We can stop at any time, can we, and restart it?
We can if you like.
Yeah. Well, I'm just saying.
Yeah, I mean, this will just hopefully feel like I'm filming right now, as a matter of fact.
Okay.
So I appreciate you letting me come over here on this beautiful
anytime.
Wednesday
Happy to have
morning.
you.
How long have you been in Tucson, and are you affiliated with the university in town?
No, I'm not affiliated with the university at all anymore. I was at one time.
Okay.
And I guess we arrived here in 2007.
Okay.
So we've been here almost 15 years.
Yeah.
15 years in October, I think.
Sure. And what was the association when you had it, the affiliation with the University of Arizona? Were you teaching or doing?
First, I was a research scholar,
Uh-huh.
and then I was a research associate.
Okay. And, you know, Bob, you're such a mystery man to me. I hardly know anything about you. I read all this amazing stuff. I start in 2009, I guess. I've spent the most time on what I think is that first major paper that you did. Is that a good place to start? And how much have you evolved in your thinking since 2009?
Well, 2009 sort of started the Courtieran work.
Yes.
Or the publication of the Courtieran work.
Okay.
Which probably started in about 2004 or so. Spent 2004 working in Venezuela for Hecla Mining, was doing some exploration work there.
Okay.
Of course, there's a whole 20 plus years of work in northern Canada in Watmay origin.
Well, not of course. I don't have your story, man. Yeah. I got to piece this together. But before we get into the background, because I do want to hear about your background, like, how do you, when you talk to a stranger and they say, well, you know, or somebody in geology, let's say, and you're trying to describe what you've been publishing on the Cordillera for the last 15 years, let's say. I mean, you're out there. Those ideas are, nobody's writing similar to you, or is that not accurate? Do you have other folks who are writing regularly in the way that you're writing?
No, I don't. I think that there have been some. Uh-huh. Steve Johnston, of course, in Canada. Okay. He's the chairman at University of Alberta now. Yeah. In Edmonton. And no, I don't think so really. I think a lot of people need grants, and it's hard to get money to do something that's considered oppositional to what the general model is. I mean, don't forget this model of retroarc thrusting and eastward subduction has been the reigning paradigm since 1969. You can go back and read Bill Dickinson's summary of the famous Asilomar meeting on plate tectonics and at Stanford, and it's the same model as today. I've recently reread it again. Excuse me. Yeah. And so no, there's not a lot of people doing it, but you know, Sam Bowering, my friend and longtime collaborator at MIT, before that Washington University, he sort of challenged me years ago, back in about 2004 or so, maybe even 2003, and I hadn't really been doing much geology. I sort of had dropped out a little bit and decided I wanted to do landscape photography. So I bought a 4x5 camera and traveled all over the country and the world and took photos, and it was fun, and I learned a lot. But he challenged me. He said, look, why is it that we have rocks in the Cascades that are so deeply buried, the Swakane Gneiss, for example, and yet they're at the surface so quickly? How can you do that in an arc? And I said, I don't think you can. And so that sort of started my thinking about the Courtier. Of course, I went to university. I did my undergraduate at University of California, Santa Barbara.
Okay, yeah, let's do it. Let's do the background here. This is good.
And so I was there in the 70s, and you know, and got a good education, and then ended up going to grad school at Memorial University in Newfoundland.
Oh.
So I went from Santa Barbara to Newfoundland, about as far as you can go on the continent. And I had worked as a volunteer for Paul Hoffman mapping the east arm of Great Slave Lake.
Okay.
And 1976, it was a 5-month field season. It was really good. I enjoyed it. And he sort of said, well, you know, if you want a dissertation, we can probably find you one and get it funded by the territorial government. So I did that, and I got funded and started doing a dissertation. And then I went around and I was particularly, go back, I was particularly interested in volcanic rocks, and I had come under the arm of R.V. Fisher at UC Santa Barbara, and Cliff Hobson, who both worked on igneous rocks, and I was fascinated with them. And I really wanted to see areas where plutons had come through. I wanted to know what that was like. And so I went and worked in this 1.8 billion year old area called the Great Bear Magmatic Zone, which is in western Wapime origin on Great Bear Lake. And so I did that, and then I decided, well, okay, I'm going to go around, I'm going to go to grad school. I got a fully funded project, and I'd go talk to Dick Armstrong at UBC. It was an obvious choice. He said, well, you know, if you come here, we'd rather you did an isotopic transect of the Coast Batholith. I said, no, I'm going to do that. I got a project. And so then I talked to people at UC Santa Cruz. I thought, well, that might be good, you know, and they said, well, we have projects and so forth. And so I said, well, I got a funded project. That's what I want to do. So I quickly found out, of course, it became a little bit disillusioned that people didn't care whether I had a funded project or not. And so it was a little bit enlightening, you know, at the time. And so I sort of didn't do anything. I would go up to the Northwest Territories in the summer, and then I go back to Santa Barbara, and I ran a record store. And I did that for a couple of years, and then finally the survey in Canada said, no, you can't do this. You need to go to grad school. We're going to support you for a dissertation. So I said, okay, I'll go. So I applied to Memorial and got in and had a full fellowship and went to Memorial.
So Hoffman was your main thesis advisor?
No, no, not at all. Brian Fryer at Memorial was my thesis advisor. Mike Easton, who's with the Ontario Geological Survey, he and I were both working in Wapime as grad students, and we both went to Memorial at the same time, 1979, and we both graduated in 1982. And Brian Fryer just left us alone. They had great equipment because of the oil boom in Newfoundland and so forth, so they had great mass spectrometer and XRF, and everybody got good funding, and so he just let us be. And
so, for lack of a better term, at this point, you're traditional, or you're not, thinking big and thinking about challenging the Hamilton model and all that. I mean,
I had nothing to do with the Courtier. In fact, I even though I went to school and I took grad classes from Cliff Hobson in Mesozoic California, 2 of them, and we traveled all over California every weekend. They were all grad student classes, but I was an undergraduate, but I was done with my undergraduate program, so I was able to do that. And so I knew a lot about Mesozoic California, but I never understood the Cordillera, so I left it alone. And I was working in Wapime, and Wapime turned out is one of the best examples of Precambrian orogenic belt.
Okay.
It has most of the features that you'd like to see. And so when I was finishing up, John McGlynn who was the division director of the Precambrian division at the survey at that time, said, well, if you can get done by next June, I'll give you a job. So somehow I managed to get done days before I needed to be done and defended. And got a job working with the survey in Ottawa.
I see.
And I did that. I mapped two degree sheets, two and a bit more of 2 degree sheets while I was there, and up until 95, and then they had cutbacks and so forth. And so I left and came back to the States, and decided that I wanted to do something else. So I did. I became a large format landscape photographer, and did that, and made a bunch of money doing that, and traveled all over, and got in fights with bureaucrats about what they would let me photograph and not photograph, and like going to Angkor Wat and stuff in Cambodia, and so I had a lot of fun. I was doing that, and then Sam sort of was trying to pull me back into geology, and because we would talk daily basically, and so
let's explore that, because you're probably aware I'm working now with Michael Eddy, who's, I think, Sam.
Oh, I know Michael Eddy, yeah.
Sam's last student at MIT.
Yeah.
And so I've been hearing a lot about Bowering. Never got a chance to meet him. Passed away a few years ago, as I understand it. So Bowering's trying to get you back into geology. So you go way back, and he's constantly kind of keeping you up to date on his work, or?
Well, yeah. I mean, I was sort of paying attention to what he was doing. I mean, I'm just trying to think. I think it might have been must have been when I was doing finishing up my dissertation and doing some field work. He came up as a grad student from University of Kansas with Randy Van Schmoos. And was going to do, Paul Hoffman had gotten together with Randy Van Schmoos and figured out that they would have he would do the dating, uranium-lead dating, because we didn't have any dating at the time. And so he came up, and Sam hit it off with us, and he spent a lot of time in my camp, and then Paul and I hooked him up with a project to do. And so he was mapping a little bit north of me, so we were famous actually for our radio skeds at night, the Sam and Bob show, as it were to be called, where everybody for 1,000 miles could listen in on our conversations, and so yeah, and then he came and worked on my projects actually, and he'd spend a month at least, and then after he found the world's oldest rocks at a cast, I went over there and spent a summer working with him on the world's oldest rocks. And so, no, we just continued on. We were both interested in the origin of continental crust and crustal recycling and those kinds of things. So
I'm imagining you guys you're talking daily, you're long lost friends, and Sam keeps saying, hey, we got to get you back into thinking about.
No, he would never have said that. No,
Okay.
no. He just let me be. And I started to. I guess I got a job through another friend working in Venezuela for Hecla. And I went down there as their geologist working on their projects, and I came away with a new model for the Guyana Shield. What I found was that, the old model was that you have all of these basaltic and andesite piles piled up on top of an older basement. But everybody had missed the fact that there was a quartzite unit that sat on top of the basement, and on top of that quartzite unit was a maybe 5 to 10 meter thick myelinite zone. And so I said, well, wait a minute, these so-called greenstone belts, they're all exotic, they're galactinous. And when I first arrived there, everybody said, oh, all this gold, it's all in these thrust faults. And I looked at these faults underground, and they had like 3 to 5 foot thick bull quartz. I said, I don't know about them being thrust faults. That's a lot of space. And by the end, I had mapped these thrust faults. And when you rotate the regional thrust faults back to nearly horizontal, all of those reverse faults rotated back to normal faults, which made a lot more sense. So I wrote a paper on it, and Precambrian research. And So I had sort of started to come back a bit, I guess, and Sam was pressing me actually the year before I went to a GSA meeting in Seattle and gave a talk on Watmay. So I was starting to come back, and he sort of, started to ask me more questions about what he was doing and how he was doing it. So it sort of pulled me into the Cordillera. I never understood the Cordillera. And most people, I think, all over the world don't understand the Cordillera.
Well, that's really why I'm here, to focus on the Cordillera. I love the backstory. Thank you for that. That's very helpful. And so I really don't know what to imagine for you. You've mentally kind of said, okay, I'm back, I'm all in.
Right.
I'm going to spend all my energy. You're incredibly well read on everything it feels like everything that's ever been done in the Cordillera, all these little postage stamps of mapping and data, and it feels like you're coming in from 40,000 feet and just saying, look, you're all missing these connections that are clear to me. So was there a moment in 15 years ago where you said, look, I'm going to get all this down?
No, not at all. I think that, I mean, I've been very influenced by Paul Hoffman and his sort of way of working. And a lot of scientists have a philosophy where if somebody has an idea or something, they'll sort of attack it and say, well, what about this? What about that?
Right.
Can you test it? Can you do this? Can you do that? Right. And Paul always says, that's a really good idea. How can we test that? What are the implications of that? And so I learned early on to sort of pay attention to concepts and ideas. And okay, if it's an idea, okay, we can test it. We don't have to just throw it out.
Yes.
And I also when I was at Santa Barbara, I came under the wing of Preston Cloud, and he sort of pushed the same sort of notion on me. So I think early on in geology, I've always understood that we shouldn't just trash ideas and models. We should explore them and see where they go and follow them. And if they're right, we'll keep going. And everybody's model turns out to be wrong in the end anyways. And so, and somebody was asking me, and I was just telling my friend Steve Wisnowski last night, we were talking about field mapping in our work in the past. And I said, Steve, if somebody can go to one of my map areas where I've produced a map and say, oh, I know why Hildebrand called it this, I'll be happy. Because ideas and everything changes, but if they can at least understand why I did something, then I feel like, okay, that's good enough for me. And so I think that I've always been a voracious reader since I was a kid. I mean, I'll read anything. I'll read Women's Family Circle or what. It doesn't matter. I think it's my escape really from reality, and so I just read. And you can go in the house and look at my library in there, and you'll find books on everything from whatever. I'm reading a book I'm very interested in how mankind is spread over the world. And I'm reading a book now by Jennifer Raff called Origin, her new book, and so I don't know. I just read, and I'm a sponge for information. So,
well, the kind of reading and then synthesizing and coming up with these amazing visuals. I'm going to show our viewers right now. This is, I wrapped up this series of live streams this past winter, and I've been pretty much just cuddling up to this every night, Bob, and I've been just, a few paragraphs at a time, and got my notes written out. So I confess that I want to read all of your stuff. So here's the glossy guy. So are there essentially a handful of major publications, can we say, starting in 2009? This is one of them. How can you describe just kind of your major publications on the Cordillera in the last 15 years?
Well, let me go back and finish our last subject with one more point that I want to make, I think. And that is that I was just like 2 doors down my office from where Paul Hoffman was doing the DNAG compilation.
Okay.
And of the Canadian Shield, and actually North America. He was compiling the all of North America.
Can you help us with the DNAG?
Yeah, a decade of North American geology by the Geological Society of America. They published like 40 volumes and had magnetic maps and gravity maps and everything for North America, and they were published in the early 80s to mid 80s.
Hoffman's 2 doors down.
And yeah, he's got one of our workrooms, and he's compiling the geology. And so I thought about that, and not consciously, but subconsciously I understood that, you know what, you can go and do anything, and you just have to study it, and you can figure it out probably, but you can make some progress.
Yeah.
And just like doing a dissertation, when you've done one and you know that when you do that, you don't really know all that much, and you're kind of nervous and you say this, but you do it.
Yeah. And
it just takes a few years.
Right.
So I wrote the first paper in 2009.
Yes.
On the Courtier, and that came directly from Sam's questioning. How do you do this in an arc? And I noted that I couldn't find any arc rocks on North America. But I saw that there was a big thrust belt. And so I said, well, if we're going to have an arc with retro arc thrusting, which has been the reigning model since 1969, and maybe earlier, we should have an arc. and I couldn't find one on, the Cascades is outboard of North America. The Sierras is way outboard, of North America. And so I said, well, this doesn't work for me. And of course I have come from Watmay and was influenced by the geology there, where we had a good fold and thrust belt, and we had a hinterland belt.
Right.
With a whole bunch of plutons and metamorphism and stuff. And
sure.
So, and the relations were pretty clear. So that's how I got started in it. And so the first paper was really just sort of a challenge, really. I didn't know all that much. I sort of worked on the hinterland belt and the thrust belt, and sort of showed how this thrust belt, went through North America, and how it had a hinterland belt just to the west of it. By hinterland belt, I mean an internal metamorphic plutonic core, which all origins have, because when you have a collision, you thicken the crust during the collision.
So for our viewers that have been watching many of these things, Bob in 2009 is talking about westward subduction. He's challenging the eastward subduction, the always Andean margin that we've been talking about for forever. But you're not dealing with Karin Siglock or anybody else doing tomography at this stage.
No, although every time Paul Hoffman, when I would talk, he would say, you need to pay attention to the mantle tomography. And I always had it there. It was, and I wrote a paper in 2015, I think, in the Hank Williams volume of Geoscience Canada, in which I did deal with the tomography right after Karin Siglock had done it, and tried to correct some errors of the paleomagnetics that were involved. But no, Sam Bowering and I were both working in the Great Bear magmatic zone, and what we learned there was that the crust is not necessarily thick in arcs, a la the Andes.
Yeah.
So, and we wrote a paper in 1984 on the Great Bear.
1984, really? Okay.
Yeah, in which we argued that arcs were generally zones of subsidence. And since then we looked, and this is very much something that Sam and I did together and talked about constantly, was that arcs are not like the Andes. The Andes is the outlier. So if you want to, using the Andes as a model for arc magmatism would be like using Yao Ming to estimate the average height of the Chinese people. Because you go all around the world, and you look at the active arcs today, and you'd say, okay, let's look at the Cascades. Well, Rainier's at sea level. There's no thick crust there. I mean, we're talking isostasy here, and that is that, corks float up, and when you thicken the crust, it gets higher and so forth. And so the Cascades, it's built on a little topography, but basically it's not high standing. And then you go on up to the Alaskan Peninsula, volcanoes are in the water of Anchorage, and the whole thing is low standing. You go to Kamchatka, And what you find is at Kluchevskoye, 16,000 feet high, is sitting in huge graben, and they're all at sea level. Japan, everything's pretty close to sea level. You can go to New Zealand, of course. It's an arc, and it's extending, and everything's at sea level. Sumatra is also built on continental crust, and it's really low standing. Sulawesi, another example. Central America, the Nicaraguan, Guatemalan Graben that's where all the arc volcanoes are. It's at sea level. You go to Italy, and Vesuvius is on the coast. It's right there. The Hellenic arc in Greece. Santorini's in the water. So this notion that arcs were high standing just grated on both Sam and I, because we don't think that they are, and I didn't know at the time. I still am not 100% understanding of all of the Andean geology, although I've dabbled in it over the years.
Yeah.
But when you look at all the arcs, you can take like 20 odd arcs or whatever, the Antarctic Peninsula, another one. And they're not high standing. They tend to be marine, shallow marine. And in fact, if you look at the Peninsula Ranges, Batholith in Baja and southern California, the Alocitos arc is interbedded with marine sediments. It's got hundreds of meters of carbonate interbedded. Same with the Sierra Nevada. You look at the Sierra and Arc rocks, 130 to 100 million a year, they're interbedded with marine carbonates. So you could show that the crust was not thick in those areas when the volcanism was going on.
And you were writing a bunch about that in 2009, beautifully laid out. And I'm guessing what you've just said for the last 5 minutes, you've said to many people.
Absolutely,
over the years.
yeah.
And what is the reaction from people? They're just fiercely defiant to what you're saying? And
No,
I wasn't
no.
taught this in my graduate student days, so how do they come back and say, no, it is really thick crust?
No, they generally don't. Everybody's stuck in their own world in life, I think, and so I think that, when somebody says you can see people's, if I talk, let me expand it. So if I talk about the Courtier to people,
right.
I've spent a long time studying the Courtier and reading about the Courtier and traveling all over the Cordillera, and I've spanned 3 countries, Mexico, the U.S., and Canada, and most geologists have not been over that area.
Correct.
And so you talk to Canadians, they'll say, "Oh, I don't know anything about the U.S." And you talk to U.S., "Oh, I don't know anything about Canada." So people just, their eyes kind of glaze over because they get information overload.
Yes.
And I just kind of walk away and.
or is it the opposite? Instead of information overload, are they just not even listening or reading your stuff?
Well, it's never it's never certain whether people read or not. A lot of people. Some people tell me that people are purposely not citing my stuff, but I have no idea whether they are or they're not, but I get that message from people. And
why would that be?
Well, I don't know, because maybe not to call attention to it. They don't like the model very much, but the same things you can look back in science, and I've tried to understand that. I've read about Wegener and how he was treated. Not that I'm like a Wegener character by any stretch of the imagination, but you can learn how scientists have treated one another. And Max Planck once said that science proceeds one funeral at a time. Mm-hmm. And so I'd sit with Bill Dickinson at Arizona Geological Society meetings, and he didn't believe in the paleomag. He just plain didn't. And your interview with Merle Beck showed that, because he talked about Bill Dickinson and what he believed and didn't. And he was here, and I'd sort of chide him about it during dinner. I'd sit next to him sometimes, and
Dickinson?
Yeah, and chide him about it, and then he'd say, "Well, you don't believe in detrital zircons." And I said, "No, I believe in detrital zircons, but I think they need to be interpreted with caution." And the same with paleomag. You need a lot of data. Yeah. So I think that everybody sort of gets stuck. And when you go into a new area, I hadn't worked in the Courtier. I mean, I had some experience in Mesozoic California because I'd seen a lot of those rocks. But I had never worked in the Courtier. I didn't understand it, and I don't think most geologists understand it, at least that aren't working in the Cordillera. They look at this thing and go, "Oh, what is this?" because there's no really good coherent story. It doesn't make a lot of sense.
So you publish in 2009, and you have every few years, maybe every year since that time. When you're doing all this writing and you publish these beautiful figures and these beautiful maps, is there reaction? Or do you not anticipate any reaction? Like, I would think you'd put all this time and energy into this, you'd expect some kind of, or at a talk or whatever, like this big ripple effect. Oh my God, what is this guy saying? This is crazy. I mean, for those that are unaware of your work, you're talking about a ribbon continent out in the Pacific and North America slamming into this thing. It's so against the grain. Is there a reaction to all this work? What's the reaction like, if there is?
It's, I don't know. You'd have to ask those people, really.
Well,
I just do my thing, and
well, let's go there. What motivates you then to keep publishing on this? If you feel like, what keeps you going on this?
Okay, people that are open and interested in seeing science proceed, and not being stuck in a bog of their own making, really, and people like Eldridge Moores, for example, who loved what I did, and his passing was just shocking, I used to spend time with him, and my daughter loved Eldridge too, because he was so kind to us generally, and because I was a research associate for several years at UC Davis after being here. But so Eldridge, and Sam, people like Sam was always encouraging me. Hoffman always encouraged me, of course.
Yeah.
And I don't really know. I mean, Cliff Hobson. Cliff Hobson was the igneous petrologist at UC Santa Barbara, and I had him for metamorphic and igneous petrology, and he's always been highly thought of, although he didn't write much, but he was a wonderful educator.
Yes.
You could turn in a thin section report, a 1 page or 2 page, and you'd get 5 or 6 pages written back about it. And so he was wonderful. And I still talk to Cliff periodically. He's 94. His wife died a couple of years ago, and he's been hiding out because of COVID, but he's very lucid and so forth. So, but he sent me a 6-page letter a couple of years ago, in his usual fashion, and in there, he basically said, "I really like all of your monographs." I sent him all my monographs, copies of them, and he said, I always like reading them. He said, "I don't know if they're right or wrong, but I really like reading them, and I'm amazed that you go over this ground that thousands of geologists before you have been over, and you find something new, and you can see new things in it." And like he says, "I don't know if you're right or wrong. That's for future to decide, but this is the way science proceeds. People have new ideas." And so I take some kind of solace in
Yes.
people that I admire saying, "No, you're doing the right thing." And then I also have a friend, Kees van Staal, who worked for the Canadian Survey. He's retired. He worked in Newfoundland and completely overturned the geology of Newfoundland. And it took him probably 15 or 20 years to get his ideas accepted. And so I'm not the lone wolf. I happen to be sort of one of the lone wolves in the Courtier, but
it seems like it. Yeah.
Other people are I've been doing other things elsewhere, and so. I don't know why I do it. I do it, partly because my daughter's been in school, and I'm retired, and so I just hang around, and I got to do something.
Sure.
And I could travel, but she's in school, so I'm not traveling, and my wife's working, so I just hang out and research and write, and I've found that, of course, that over the last 40 to 50 years, that there's an incredible amount of data just sitting around, and it's widely underinterpreted. And
I'm loving what you're doing. I mean, I'm here on vacation, and I would definitely wanted to spend 90 minutes just chatting with you, because I think I agree with Cliff and many others. I can see what you're doing and the promise and I mean, in my own small way, I'm trying to do what you're doing. I'm trying to make these connections, to sew these connections between these various things. And I don't know if my motivation is not to upset the apple cart and just turn it on its head. I don't know if that's your motivation.
No,
either.
not at all.
No.
I just don't understand the Courtier, and I've been trying to understand it, and so I keep poking away at things that I can gather and information, and you know, I don't really like my first paper on Western subduction now, and I
what has changed?
Well, just my ideas have grown. I know a lot more about the Courtier. I mean, I still think Western subduction is correct.
Okay.
But, you know, I know a lot more. I know a lot more about the Jurassic and the Cretaceous and how some of these things fit together. And I didn't have any idea about that. I would say that working with Joe Whalen has been really good for me. Mm-hmm. And Joe and I were in the same division at the Geological Survey of Canada. He worked in Newfoundland and worked in the Shield and places, and he's a granite guy, traditional granite guy. Mm-hmm. And I was kind of, after when I was mapping and doing this work, I was kind of a granite guy, volcanic and granite guy. Mm-hmm. And we both always believed, granites come from the crust. And Sam Bowen always believed granites come from the crust. But, you know, Joe and I decided after he retired that we wanted to start working together, and we both had ideas about slab breakoff. He had those ideas in the Newfoundland Appalachians, and I had developed those ideas with Sam in Watmay. Mm-hmm. And so Sam and I figured that a lot of continental crust was recycled when you had arc continent collisions, for example, because when the oceanic plate tore away, mm-hmm. A certain amount of continental lithosphere was also subducted. So you were recycling a fair bit of continental crust. All the time. Every time you had slab failure, you recycled some amount of continental crust. Yeah. And so Joe was working on slab failure and arc magmatism in Newfoundland. So we said, well, let's sort of work together. So we attacked the coastal batholith of Peru. He wrote a paper in 2014 on the coastal batholith of Peru. And we found we couldn't get there weren't any good analyses. They were very dated and they weren't very good. But we did understand that the coastal batholith was, which people had like Wally Pitcher and others had called a marginal basin, was in fact 7 to 9 kilometers of arc magmatism. Again, shallow marine. Shallow marine. Yeah. And that's the Calipui. And so we said, okay, and we wrote up a paper on it in the Paul Hoffman volume, and we were invited to contribute to that. And so then when we started looking at the Peninsula Ranges batholith. And that was mainly because years ago, some guys had collected on a grid samples of rocks all over Southern California. And Sin-T Lee, who's a professor at Rice University, mm-hmm. he got his PhD at Harvard, had published a paper on the origin of continental crust in the Peninsula Ranges, and he took a lot of this data from the Peninsula Ranges. Wasn't very well sorted, but he reanalyzed all of the samples using ICP-MS. Mm-hmm. And so his neighbor was a guy named Morton, an old Geological Survey guy, and I think he was at Pomona or Riverside or somewhere after he retired. Anyways, I contacted him, and we sort of sat down and worked our way through which were samples that came from marginal zones. He had the original 50,000 maps from these collections, these data collections. Mm-hmm. And so we were able to take that data and sort of throw out all the junk, the stuff that represented mixed zones and wall rock xenoliths and all kinds of stuff. And so we took those data and we found, well, they don't look all that much like arc rocks to us because we had the Alocitos arc there. And then we noted that oh, look, there's a major deformational event in about 100 million years. And it was well documented by Wayne Primo and others, and Morton himself. And they just published at the time we were doing this a 1,000-page volume, a GSA memoir on the Peninsula Ranges, which was, they called it a data dump. They had all this data and all this stuff. And so we actually ended up, we had the table of contents from that, and I got all the papers from pretty much everybody. So we decided to write up a paper on the Peninsula Ranges, and because we found that the geochemistry of the post 100 million year rocks, in other words, the post deformational rocks, were different than the pre 100 million year rocks. Quite different in terms of trace elements. And so we developed a series of discrimination diagrams. And we published that paper also in the Paul Hoffman volume. We published 2 papers in that volume. And so that's how we got going on the Courtier and slab breakoff stuff.
Is that an example of how you've changed from 2009? I don't remember in the 2009 volume or paper that the 100 million year event was.
We didn't recognize it at that. I didn't recognize it at that time at
Okay.
all. I hadn't recognized it at all. It was the Peninsula Ranges and understanding that there was this major deformational event at that time, and we could separate out the plutonic and magmatic rocks to pre and post collision. We interpreted that deformational event, which is regional. I mean, it's a regional event in Mexico and Southern California as an arc continent collision. And we found through the work of Mexican geologists and my friend Tim Lawton that there was a basin which had opened up sometime in the early Cretaceous. And this basin was called by Mexicans the Alocitos. It's called the Bisbee Basin in southern Arizona. And that this basin had a west-facing carbonate platform. So it had a continental margin on its east side, and it grew up, but it faced an ocean to the west. And this was developing at the same time the arc was growing on the other side. And so we said, well, it's pretty clear that this is westerly subduction because we have the passive margin and the thing closed up with the arc as the upper plate. So that's how we first sort of thought about the 100 million year event. We hadn't really seen it. We hadn't known about it. And then, you know, we realized, oh, wait a minute, Sierra Nevada, it's got the same thing. It doesn't have the basin was well preserved, but it's there, pieces and fragments of it. But it sure has the arc and the post-collisional rocks. And, you know, we kept on tracing it through Nevada, and we found it. We found it through the Cascades and up through the Coast Plutonic Complex into Alaska. And so that sort of culminated in a couple of papers we wrote for Canadian Journal of Earth Science published last year on what we call the Peninsula Ranges Herogeny.
Got it.
And that's sort of a response to I called it a kerfuffle in the first paper, actually, between Karen Siglock and Terry Pavlis and Sarah Reski and a number of people who wrote a GSA Today paper saying that we didn't look at the geology and neither did Siglock, and we didn't pay attention to what they knew. So I said, well, in my sort of overkill way, I said, I'm not going to write a reply. Karen wrote a reply, and I said, I'm not going to write a reply. I'm just going to show our hand and show that we have data going from southern Mexico to Alaska. Never mind this little bit in Alaska that you're working on. We have a more extensive data set. I get irritated when people say I don't do my homework, because I think I do.
Yeah.
And so. We wrote a paper, a big paper, and the editor of CGIS said, oh, you've got to divide it into two papers, it's too long. So, of course, we spent all this time dividing it into 2 papers, fixing the references and the things, and then they published it in the same volume back to back. So, okay, that's fine, whatever. It makes it easier for people to send them around or whatever, So that was kind of fun. But, so that was sort of what, well, okay, I'll show you. We have some pretty good data set, and I think that the 100 million year event, now Basil Tikoff loves it. He's taken off with it, and other people have taken off with it as well, and so I think it's growing. We just submitted a paper on the Western Interior Basin, showing how it ties in really well with the 100 million year event.
Okay.
We'll see how that goes. It's submitted to Geosphere, and it's always a crapshoot as to who reviews it and who edits it and all this stuff.
So with your current thinking, what's the chronology, basically, of westward subduction, and then we turn to eastern subduction?
Well, as I understand it, and like I say, I don't know everything, and I've mainly worked on the Cretaceous because the Jurassic you can't work on the Jurassic, I don't think, until you can understand the Cretaceous, because you've got to go back in time. And if you had basins opening up in western North America that go the extent of North America, that are following the classic Nevadan orogeny at 150 or 153, whatever it was dated at best now, latest Jurassic anyways, this basin opened up, well, then how can you possibly understand the Jurassic if you don't understand that there's this basin that opened up? So, you know, it kind of solves part of the problem. There's been a long-standing debate in the Canadian Cordillera, and it's kind of swept into the northernmost Cascades as well, and that is that the intermontane terrain collided in the Jurassic, and other people say, no, it collided in the Cretaceous. Well, Joe's and my model allow for it to have collided twice, because of course it could have docked in the Jurassic. You have this spreading event which opens up the sea, and then it collides again in the Cretaceous. So it becomes complicated, and people haven't, I don't think, come to grips with the implications of that. So there could be a piece of the formerly accreted intermontane terrain that got broken off, and it's now with the insular terrain, and it's on the other side, and maybe little bits and pieces of the insular terrain are left on the eastern side. And then when you bring them back, did it come back in the same place? Maybe, maybe not. It would require quite a bit of detailed work to know that. I don't think it did. That would be extremely unlikely. But so you can't just grab a piece and say, look, intermontane belt. It's clearly here, because there's 3 Jurassic collisions that you can trace, and you can trace those in the Klamaths and in the westernmost Sierra Nevada. There's one at about 170 million years. There's one at about 160 million years, which seems to be the biggest one. And then there's the last one, which is the arrival of the Mariposa or the Rogue Chetco in the Klamaths. And all of those are arc terrains. So they've all had involved westerly subduction, whether if you recognize them, and it's not my work. I didn't do the detailed work on those terrains. It's published, it's widely accepted. And these are arc terrains. So you've had westerly subduction throughout the Jurassic, because arc terrains are coming in. It's not, they're not arcs that are native to North America, although some workers think they are. But the people that work, like Eldridge and other people, have long argued, no, these are arc terrains coming in, and they have deformation. And after each collision, you get a bloom of plutons, which are readily interpreted as slab breakoff or post-collisional plutons. And with each one, after the 170, you get these, and after the 160, you get them, and after the 153 Nevadan collision, you get them. So it fits our general idea of collisions and magmatism. And then you now open a basin after that. And then you close it at 100 million years.
And is that the end of the westward subduction at 100 with your current thinking?
Well, I think so, but I'm not sure. And the reason for that is because there's another major deformational event which people tend to gloss over, and that's the Laramide. And there's a major thrust belt which comes up out of Mexico and then turns westward and goes across southern Arizona and goes all the way out to the Coast Ranges. There's high-grade Cretaceous rocks in the Los Angeles area. And the San Gabriel Mountains, for example, that have long been recognized. And there's a whole bunch of plutons that trend east-west, interestingly, through the Mojave region that are, say, 97 to 84, the same as the Sierras and the Peninsula Ranges. So that's sort of, you know, I'd sort of been poking around trying to understand why there were so few thrusts related to this, what people called the severe event, which was a 124 million year collision that's widely recognized up and down the Courtier, and it's what Dick Armstrong originally called the severe and picked it up from other people. But there's like only one thrust. And I said, well, where's the rest of it? Where's the rest of the origin? Where's the hinterland belt? Where's all the plutons? And then I looked and I said, oh, wait a minute, there's a belt in Canada called the Omanika Belt. And it's sitting up there, and it's got all the right age thrusts and magmatism, but the thrusts in the foreland, they're not the right age. They're all younger. They're Laramide. So I said, well, shouldn't we just bring that back down then? And so that's sort of how I got into the Baja, BC sort of discussion is because I said, well, no, the geology doesn't match. But it matches if you bring this back, then you do it. And nobody's had a good explanation for the Omanika belt. They've always, the Canadians say, oh, we got these two magmatic hinterland belts, and this one's here and this one's here, but so it didn't match. So of course I looked into the data sets and said, well, it's permissible. And I sort of left it like that. I said, no, I wrote a paper on it, actually. I included it and said it came back and showed how the pluton's here and the deformation there, and that was in the in Geoscience Canada, I think in the Hank Williams volume. Hank Williams was sort of Mr. Appalachian Geology, Mr. Newfoundland Geology, and he was on my committee when I was at Memorial. So he and I hit it off because we were both doing regional mapping projects, and so I very much liked him, and everybody liked Hank, and so. I sort of moved forward with thinking about that and what you could do with it.
Yeah.
And I think in my next big paper, which was 2013, which was more of a overview paper of the Courtier, it's called Mesozoic Assembly of the North American Cordillera. Yeah. There I made that argument quite straightforwardly, talked about how the Swakane gneiss and the Oricopia joined up with, then they're young, they're 75 million years or so. And talked about the various places where paleomag had been collected, and I began to realize that the Baja BC was in concept a really good concept, but it couldn't work. And what I mean by that is that here you've got the paleomag for the Cordillera. A lot was collected in the Western Cordillera. Yeah. There are samples collected in say, in the Blue Mountains and right up against the Tintina Fault in Canada, and they also showed the same kind of northward migration, 1,600 plus or minus 400 or 500 kilometers. And so I said, well, look, here's all these guys that are a lot smarter than me. They're working in the Cordillera, and they all say this Baja BC thing, but they can't find any faults. And they don't have any piercing points. Nobody's ever had a good piercing point, and that's why people who work on the Nanaimo group try to bring the detrital zircons back off of the Mojave and stuff like this, because they're scratching for piercing points. And I just don't think it's so easily demonstrated by detrital zircons. You need pretty clear point sources. For example, the Florida Mountains has intrusions that are about 509, 510 million years, and you see them in the Tapete sandstone, the basal sandstone of the Cordilleran passive margin. You pick them up right away. They're there, and so Matthews at Calgary has shown that, and a number of other people as well, and so surprised people how young the Tapetes was actually. But at any rate, so you can do it if you get a good point source, and you can document it. But there's all these guys who've been working for 25 years on trying to find out what's going on with Baja BC. And I said, look, you're looking in the wrong place. You're falling for the old thing that you keep doing the same thing and expecting a different result. And the saying goes for that if you keep on pounding your head and expecting a different result, that's the definition of insanity. And I don't think anybody's insane. I just think everybody's got their area and they're working on it. But I said, well, wait a minute, it doesn't make any sense. We have data that suggests that right up against the Craton, things have moved as well. So why don't we start there? Why don't we look at the faults there and see what we can find?
Look
because
further east.
so there are big faults there. There's a whole fold and thrust belt. There's major cutoffs and major things that everything just changes, and the Cordilleran Maya geocline is just cut off, and there's other rocks just sitting against it that throughout Nevada, for example, that don't seem to have really good arcs and aren't really things aren't very well understood. And the recent work by Bernie Housen at Western Washington shows, the Blue Mountains, that's got 1,600 plus or minus 400 kilometers. It's moved north, and the work by Randy Enkin in Canada. The problem is that all of the people who are, I call them fixists in a way, who don't want to have large-scale migration, who objected to this idea, sort of drove most paleo magicians or magic people out of the Courtier.
Yeah.
They didn't want they got abused, really. I mean, they were threatened. They were told their work is hogwash, and you know, it's shocking, really. I mean, these are supposedly professional, open people, and
Right.
and I don't mind, you know, telling them off a bit, because I think it's wrong.
Mm-hmm.
And I think the correct way, as I mentioned earlier, is to say, no, embrace it. Let's see where it goes.
Right.
See what the implications are. See if we can disprove it. And so there's been this model out there that's been sitting there, neither proved or disproved, and that's why, you know, Daryl Cowan wrote that paper with different ideas and trying to explain it. But they're out there, and I think the main movement happened far inboard. And sedimentologists, a guy named Contaneu, and I can never pronounce his name correctly, who's in Alberta, showed nicely that the foredeep, the collisional foredeep, migrated from, say, about Salt Lake up to Calgary during the latest Cretaceous, earliest Cenozoic. So there's a bunch of different data to support things happening inboard. If you look at all the thrust faults, the supposed laramide thrust faults in the southern Canadian Courtier that seem to go up and peel into the Tintina Fault. And then there's a whole area where you just got the North American Craton against the Tintina Fault and the exotic terrains. There is no thrust belt. I mean, like 1 or 2 little thrusts. And so I think the Tintina was a big player. There's something happens when you get down to the Helena salient that causes some complications, and I've been trying to. I talk to Basil Tikoff fairly often late at night. We've had these COVID discussions, and where we talk for 2 hours until we're both exhausted and toss ideas around and stuff. But so this doesn't mean we agree, but you know, we talk about stuff, and so I just think that there's a lot to be done there as well. That will resolve that argument.
And do you see the same translation timing that the Baja BC literature is proposing, a kind of an 85 to 55?
Yeah, absolutely. I think there's no question. So what I did, and you have a paper there, my Geological Society of America Today paper. I think I saw it in that pile. It's called Baja. No, that's it right there. Yeah. In that paper, I went at this notion and showed how that if you get rid of the extension through the Mojave terrain and in Southern California, you bring all the laramide rocks back to about the thrust belt. And then you could slide everything northward along the thrust belt. Well, the laramide belt, which is a high-grade amphibolite-grade metamorphic belt with all of these post-80 million year plutons in it, which are slab failure composition plutons, that picks up again in the Helena salient with the boulder batholith and rocks up there, and then it goes across into the Cascades and then turns northward and goes up through the Coast Plutonic complex. And of course, that's another collision. I don't understand it. I don't know much about that there's a basin that formed or how it formed, but there's clearly a collisional belt, a whole bunch of thrusts, and you know, it's the main thrusting in the Canadian Cordillera in the eastern part, and it then, you know, you could trace it on up into Alaska. So it kind of comes up as a sigmoidal belt, and people got on this thing back years ago by a famous paper by Coney and Reynolds, in which they looked at the magmatism in southwestern North America. They looked specifically from Tucson to California. Well, as far as I could tell, the Mexican thrust belt laramide comes up and then it turns and goes across southern Arizona to California. So they collected along strike. So of course it would look like it was a flat slab. And Alan Glazner's been arguing about that as well. He's at University of North Carolina, retired now, but he's argued against that because he did his dissertation in this area as well on rocks. But so I think that's how the whole flat slab idea got started. And people have argued for that, you know, consistently. And I don't see it. I just, you know, the idea, I mean, so the idea of Peter DeSalles, who's at Arizona, and other people argue that you got these plutons, these flare-ups, they're called, because you subducted oceanic lithosphere beneath North America, and there's been such a friction between the plate, upper plate and lower plate, that you get this thrust belts 500 kilometers away in the upper crust. So they argue, well, there's been about 400 kilometers of shortening since the Jurassic across there in thin skin thrusts. So they don't explore this, but the implication now is that, well, okay, you got to balance the section.
Yeah.
So where's the 400 kilometers of middle and lower crust that go along with, that were with that upper crust? Well, they'd say that you thrust all that underneath the Sierras and you melt it. They never come up with a model for how you might melt old cratonic lithosphere with its big, tectosphere beneath it.
Yeah.
It's a lithosphere beneath, mantle-lithosphere, which is cold and pretty resistant to melting. And but you melt it, and then you get these flare-ups, and it thickens the crust, and you get this giant thing. Well, okay, but that didn't happen with the Sierra Nevada, because you can show that up to 100 million years the volcanic rocks were interbedded with marine sediment. So there wasn't thickened, and then bang, you have a switch, and then up come the other magmas by 97, 96 million years, very short time. So you don't have time to melt all of this crust. And besides, the composition of the Sierra Nevada, by these guys' admission in their papers, Mihai Duce and Jason Salibi. Jason was at Santa Barbara when I was there. I know him very well. But they say you melt this to make the Sierra Nevada. Well, it's the same composition. So you got to melt all of it. If you just melt 10% of it, you get a completely different composition. So if you want to get the Sierra Nevada, I mean, it's the 12% difference maybe, and 10% different in composition than the middle and lower crust. And so you got to melt all of it. So how you do that is just beyond me. So our slab failure break-off model and collision resolves all of that kind of nonsense. And maybe it's not, maybe it's right in the end, but it doesn't make any sense to me. It just doesn't. I don't know how you get rid of 400 kilometers of cratonic lithosphere, which is buoyant. But if you put a slab on it, an oceanic slab, you can pull it right down. That's the main difference between the standard model and my model, is that, look, I just put an oceanic slab on the end and subduct it. And that's what Karen Siglock argued in her papers, was that, look, you can do this offshore. Because if you have an eastwardly dipping slab, and North America's here, and it's migrating westward as the Atlantic Ocean opens, which we know, then you should have a trail of slab across the ground. Right. But if you're moving North America into a subduction zone, you'll get a pile. And so she noted from the U.S. array data that there's and this is not Stephen Grand knew about this and wrote about it years ago, decades ago. It's this huge fast zone in the mantle, which is generally interpreted to be a cold slab. And it's 2,000 kilometers high and some 850 wide. And it's underneath eastern North America. And she modeled it, and I've modeled it, and you can show that, yeah, that goes back to beyond western North America at the time. But everybody's not accepted that for some reason. So
for some reason. That's the part I don't get. For some reason.
Well, like I said, science proceeds one funeral at a time. It's not, people don't like change. If you go back and you read Mock Green is a clever guy and wrote a recent book on Wegener. But he's written several papers on Wegener. He says, look, first of all, new ideas, the scientists are going to respect the brevity of human life. And, new ideas are especially dangerous because they might be wrong and they might be right. And, so scientists tend to wait until somebody they approve of or really, think is deserving or whatever goes with the idea, so they can get 2 for 1. They can come in late, they don't have to read it. Right. They can just agree with the person and then they move on. Right. But he says, well, there's a dirty little secret. Most scientists don't like to read. And he said, look, throughout the entire Wegener argument, there was nobody who wrote anything that indicated that they had read Wegener in detail and that he understood him. He just said it's like they hadn't read it; they just were against it. And I've you can read Naomi Oreskes' books on that, and she says, look, there's a big difference in North American geology from European geologists, and American geologists, let me go back. She was trying to understand why North American geologists specifically were so against Wegener's ideas. And yet, you know, anybody who worked in Africa and Antarctica and some, Warren Hamilton, you know, in his paper in 1962, The Backbone of the Americas, talked about how that continental drift was right and that everything fit back together. So, you know, she pointed out that North American geologists don't like it if you reason from a model. If you have a model, and they want to have this Chamberlain idea where you have multiple working hypotheses. Of course, no experiment is ever set up with, everybody has an idea and they set up an experiment to show something or deny something. Yeah. They don't have, like, you know, thousands of experiments ready to go. And so if you're arguing for a model, they don't like it because it doesn't fit the concept of multiple working hypotheses, which people don't, you know, you don't really use it when you're in the field and mapping, and you, right from the get-go, oh yeah, look, and you get, so that's sort of why North American geologists, as far as I understand it, and I'm no scientific philosopher or anything like that, so, you know, I try to read from these people that learn from these people that do think about that kind of stuff, and that seemed to what they sort of say is that North American geologists, it's this egalitarian, democratic sort of thing where there's a multiple of ideas and this all comes together, and whereas my approach was, I had this idea, and then one guy wrote to me and said, look, your idea is not going to fly. You're just, it comes across like you're cherry picking. You're not at a recognized university now. You know, you just seem like you're sitting in an armchair collecting data. You've never done any field work, and I didn't. You know, I've done map few 2-degree sheets, and, you know, right, and mapped Silver City Quad, and, you know, I spent a lot of time in the field, you know, and so I just couldn't understand where this guy was coming from. But at any rate, so there are people that, you know, seem to not like the ideas in general, and they prefer that you start with your small little area and then grow from there exponentially, where I took the approach where, no, and I don't throw out papers or anything. I look at all the papers. I don't, you know, if you go and read this, you'll say, I said, well, this person says this. Well, okay, but you can, if you don't agree with them, you can say that. You can still cite them, and you can say, oh, I don't agree with them for this reason. But that's not what most people do.
Well, I wish more people were open. You'd think if even basic reading of the history of science, you know that there's this human tendency, for lack of a better phrase. So, I mean, it'd be nice if we had people working on a higher plane, and I get the distinct impression you're not done. Are you going to continue? Is there another paper that we can be
Well, there's a bunch of stuff that I want to work. I want to understand. I want to work on the Laramide, for example. Okay. And the Basin Range provinces and so forth. You know, because it's not just that the Omanika Belt has moved northward. You know, the Basin and Range in western North America is offset from the Basin and Range in Mexico by about the same amount. Really? And the Eocene volcanics, which come down through into northern U.S., are also down there, but they're not in between. And so, you know, there's a number, not just the Laramide restores as well. There's the Laramide Metamorphic and Plutonic Belt that if you restore 1,300 kilometers, in other words, if you bring the Lewis and Clark lineament back to the Texas lineament, which were King's original dividing lines for the Cordillera. He had 3 kinds of deformation in ages in the Cordillera, and the Texas lineament formed the boundary in the south, and then you had a central region, the Lewis and Clark. But the Lewis and Clark lineament goes over to the thrust belt and ends, and the Texas lineament comes here and ends. And I said, oh, let's line them up and see what happens, because nobody's had any piercing points ever for Baja, BC. And that's what that paper you were just showing was all about. And I said, look, they line up, and if you line them up, oh, look at all these other things that match up. So, you know, there's probably 4 or 5 piercing points that appear there when nobody had any piercing points before. So I haven't proven it. I haven't demonstrated it beyond a shadow of a doubt. But I think it's a good idea, and I think people should try to understand it. And so I kind of keep poking away at that and trying to understand it. Where does the Tintina Fault go? It's got, by everybody's admission, 400 plus kilometers of strike slip. I think it's much greater, but then it just comes down and it seems to disappear. It just ends. And is it in the thrust belt?
Right.
Are the transpressive thrusts, that both have a strike slip and a shortening component? I don't know. It needs some field work. It needs some stuff that I'm not going to do, but I've put the idea out there, and hopefully people will go and test it. There are people looking at the thrusts. A guy named Ben Vanderplume and Dinu Pana. Dinu Pana's with the Energy Regulatory Group in Alberta, and he keeps going off and doing crazy good science and the Courtier just on his own. That's not his job. He's got $7 million to spend this year on stuff because from the oil, stuff. But maybe he doesn't have it anymore, but he did have it when I last talked to him. But anyway, see, they're doing some interesting stuff, dating the faults themselves.
Well, this is all good because I'm not sure if you're aware, but I like doing these live stream series each winter when I have nothing else to do. And I'm going to do a Baja BC series this coming winter, and I'm hoping to get a variety of voices involved, not just the cheerleaders, but people who are dead set against it, and everybody in between. And I would just like to explore some of this stuff. So we'll be reading your paper very carefully, and possibly you'd be up for joining us this winter.
Sure, anytime. I'm just hanging around, looking at stuff. But it's interesting because I can never understand how you can take good scientific data, good results, and just ignore them. And that's what people are doing. And I think the onus is on the people that say, no, this data is no good. Now I can understand. I'm a big believer that plutons are folded. People tend to think of plutons as being these big domical things, but I think that's wrong. I think I published a paper on it years ago, 2012 maybe, and which we showed that plutons have flat roofs and flat floors. And that makes really good sense if you think about it. Because if you're going to blow up a pluton and push the wall rocks, you've got to push an infinite amount of wall rock aside. Whereas if you just have a magnetism that comes up and spreads out like a sill, at the most you have to lift 30 kilometers. Yeah. Maybe you only have to lift 10 because you're at that place in the crust. So it involves much less work. So plutons generally tend to have flat floors and flat roofs. And the Sierra Nevada is no different. That's why there's these screens of wall rock with concordant bedding in between plutons all over the place. And Bartley and Glasner and Drew Coleman have shown that in several places in the Sierra and in several publications. So I'm not really, so you can fold plutons. If you fold the rocks, you fold these sheets of plutons. So I think I think that people have a point, and I don't really necessarily agree with Merle Beck that you could take the Mount Stewart batholith, which has been through a few deformational events, and it's clearly folded. The map clearly shows it's folded, and get good paleopoles from it. I think the right solution is to have successions that have volcanic rocks and sediments in with them, do the compaction corrections for sediments. The volcanics are your control, pass a fold test, conglomerate test, and all that kind of stuff. So, because it's hard to tell sometimes where you are in a pluton because you don't have any paleo-horizontal. And Merle Beck admitted that. I mean, he admits that and knows that. But the Mount Stewart batholith is clearly folded. You can look at it. It's folded, And that's a 100 million year event. Or just after. It's probably folded by the Laramide event. But it's clearly folded. So I'm not in favor of using plutons. And
but
I think
volcanics
and sediments can be corrected, and if you want to do compaction corrections, you can do that in the sediments, and that seems to work quite well. And where you've got volcanics interbedded with it, you can do the volcanics, and so that's why Randy Enkin's Carmack's volcanics in northern Canada are so compelling, because he's got them over hundreds of square kilometers. These things, they go right up to the Tintina Fault, and they all have 1,600 kilometers of northward movement between about 70, they're 70 million years, between 70 and 58 or whatever, and the Clarno seems to be in place in western Washington. And before that, all bets are off, but 70 some odd to 50 something is the time when they moved. And the paleopoles for the Carmacks are basically somewhere between Portland and San Francisco. And I just don't see how you can get around those things other than just saying it's bad data. And then, well, wait a minute. They've got it in all kinds of different places.
Right.
It's consistent throughout the
Right.
whole Cordillera. It's not like it's just an aberrant point, you know. And
Yes.
and so you can't just keep writing this stuff and ignoring it. And that's what everybody does. They don't even talk about it. They don't mention it. And so you just kind of go, okay, well, it doesn't work for me. So that's why I've continued to push on this stuff, is to I'm trying to understand and how the Courtier developed, and I think it's just an accretionary belt where you've had these arcs colliding with Western North America. Still haven't found an arc on North American lithosphere, and after searching for a long time, and nobody else has either. Yeah. People say, "Oh, the Sierras," but no, that's not on North America. Yeah. It's way outboard. It's 500 kilometers from the edge of North America. So, that's why I keep plugging along, I think, because I want to understand it. And I will say that I have less energy now. So I had, COVID. I may even have long COVID. I felt after COVID. I had COVID 2020, December. That's the first year was 2020, wasn't it? Yeah. In December, my wife and daughter, we all had it. And then I had some heart problems develop because of COVID, they say. Really? And so I went and got those cleaned up. And so I'm okay, but I feel like I don't have a lot of energy. This last paper, I wrote it and it was done in August. And other people said, well, you might want to change it around a bit and emphasize some things. I didn't touch it till January. I just didn't have the energy. And then finally I stopped taking some medication, actually, which I think may have had a role in it, and so I got some energy back again. And,
Good.
And so we'll see what comes down the pipe. I have no idea, where I'm going. Although I'd like to spend time on the Laramide and the Basin and Range, and I have these grandiose ideas of unraveling the Courtier, which of course will never be done. Right. But maybe somebody can pick it up from there. I just don't know.
Well, I'm hoping we can get a few more eyeballs at least on all this great work you've done. And there is a website where these folks watching this video can find all these papers and download them themselves? RobertHildebrand.com/pubs.
Okay. Would be I took some years off and did photography, so if you go to roberthildebrand.com, you'll get my photographic site, but there's a little link there to pubs. Okay. And I haven't done anything to the website in years, to the photographic website, so you can look all you want, but I haven't really updated it or done anything. But
those publications are up to date.
There's a list right there, yeah. And part of the problem is, I would like people to challenge these models and make me defend them, but that doesn't happen. They're generally ignored because, and I understand that because it's a big challenge to spend time to get up to speed on an entire orogenic belt. The Cordillera, the literature is voluminous, and I'm up on it as much as anybody probably. And there's still more that I don't know and can get into. So for people that haven't done that, it's just overwhelming. Yeah. And so when people say, well, how do you demonstrate this? I say, well, if you go up here and you look at these rocks here, and then you go down here and look at these rocks, and their eyes are like glazing over and they're kind of falling asleep, and because they don't know the geography, let alone the geology. Yes. And so many people say, well, I can't even evaluate it. Okay, so I'm sort of an island out there.
Yes, you are.
And so people, are not really, challenging me. And I'm happy to have people want to challenge me. Let's go. I'm ready to go. I got lots of data, and I'm not making this stuff up. It's there. You can read about it and read the papers that are cited, and I'm not purposely cherry picking data and not using other data. The data are there. So it's an open invitation. If you got some good ideas about the Courtier, bring them on. I want to learn about the Courtier, and I'm not going to, just say they're hogwash ideas. We'll test them.
I love it.
And what else can you do?
Hey, it's been just a pleasure, Bob.
Oh, anytime.
Thank you so much.
I don't know if it's useful, but
Definitely useful. Are you kidding me? Come on now.